Okay, our next topic is 9b, matching and assignment problems. And for this chapter, we need a few definitions again to know what they're actually talking about. First of all, we need to know what a directed graph is. Sometimes that's also called a digraph. But what does it actually mean? We have a network, and this network is using arrows on the edges to give directional information. So we record directional information on networks with the help of arrows on the edges. And when we have such arrows on the edges in a directed graph, we call those edges arcs. Good. The information of a directed graph can again be displayed in an adjacency matrix. And when we do that, you can see a matrix down here. A, B, C, D, E, A, B, C, D, E. All right, that's a matrix. But the labels here on the rows is the origin, so where the graph starts. And this is where the graph goes, so that would be the destination. So the column, the rows of a matrix are the origin vertices, and the column labels in the matrix are the destination vertices. The direction of travel is from row vertex to column vertex, of course, because the row is the origin and the column is the destination. So this is a very simplified matrix here. We almost have no entries. We have a 0 here and a 1 there. Okay, but we start with the row. So go, nothing in the A row here, something in the B row. B, D. Okay, there's a 1. That means there's one arc from B to D. Good. So there's nothing in the C row. There is an entry in the D row from D to B. Okay, but that entry is a 0, and that actually means there's no arc back from D to B. Therefore, our directed graph would look fairly simple. We have a B and a D. They're connected with an edge, and we have an arrow here as a direction. What I want you to do now is to pause the video, read example 5 on page 375, which gives you a good indication, or it shows you another nice example of an adjacency matrix for a directed graph. The next thing we need to have a look at is bipartite graphs. So what is this now? If the vertices of a graph belong to two different sets, we can create a bipartite graph. Each edge joins one vertex from one group, two vertex in the other group. And then we can also do complete bipartite graphs, which include all vertices of the second group for each vertex of the first group. All right, if this didn't make a lot of sense to you, let's have a look at example 6 together. That's on page 376. We have two groups, and one item are the presenters and the other item are countries. So we're having 5 different presenters. We have Angie, Beth, Charlie, Dorian, and Evelyn. And those presenters are supposed to go to Senegal, Vietnam, Peru, Ghana, and Myanmar. Good. So Angie is visiting Senegal, so we're going from this group over to that group, and Beth has visited Vietnam and Peru, so we're going from Beth to Vietnam and to Peru. So we do the same thing. We have Charlie for the other presenters. So we're having Charlie, and Charlie went to Peru as well, but he also went to Ghana. And Dorian went to Senegal, So there goes a line. And he also went to Myanmar. Evelyn, this last one, she went to Myanmar and also to Vietnam. Needs to go to Senegal. There's no other option for her. But if Angie goes to Senegal, that means Dorian doesn't need to go to Senegal. Okay, there we go. Because we just want to connect. We want to have each country visited once. So then if Dorian cannot visit Senegal, he must visit Myanmar. But that also means that Evelyn cannot visit Myanmar. So she's going to Vietnam. That means that Bev's not going to Vietnam, but she's going to Peru. All right, and how about Charlie? Charlie can go to Peru or to Ghana, but as Bev's going to Peru, we delete this line. And there we go. Angie will visit Senegal, Bev will visit Peru, Charlie Ghana, Dorian Myanmar, and Evelyn will go to Vietnam. Read through the example again in the textbook. Maybe it's going to be a bit clearer then, or I hope. Should be. Cost matrix. So, if we have such a bipartite graph and rewrite the weights, so we not only have directions, right, in a directed graph, we also have the weights because it's a network. And we write those weights in a table. We call that cost matrix. Cost doesn't necessarily have to be in terms of money. Can be something else. And if you have a look at this table here, this is on page 378, and that will also lead us through our next chapter. So we're having different employees here, Wendy, Xenophon, Yolanda, and Zelda, and we're having 4 different machines, and we're investigating the times and they would spend on using those machines. That's what we call a cost matrix. We will deal with this example in the next lesson and the next video again. What I want you to do now is have a look at exercise 9b, questions 1 to 5, and then wait for the next video.